We'll now look at the possibility of infinitely many solutions and how that works. So let's consider this linear system. The first step to solving it would be to put it in augmented matrix form. Since we already have a 1 in the first row, first column, we need to get zeros underneath that. One of them is already a 0. We only have to deal with this -2. So we'll do 2, row 1, plus row 2. And here's the result from this row operation. We already have a 1 in the second row, second column, so we need to get zeros everywhere else there. The top is a 2, so we'll do -2, row 2 plus row 1. And the last row is a 1, so we'll do minus row 2 plus row 3. And here's the result. So we can see something is suspicious here because we have a row of zeros. This is not like the no solution case because that last augmented column does have a 0. However, we cannot get a pivot position in the third column. And this is the clue to infinite solutions, is we're looking at the pivot positions. Since we cannot have 3 pivots here, we will have infinitely many solutions. In order to better describe these solutions, we'll talk about the different types of variables. And there are going to be 2 types. The first is a basic variable, and basic variables are the ones that correspond to the pivot positions. Free variables, on the other hand, do not correspond to pivot positions. They're the ones that don't have a pivot. So now that we know this, we can kind of expand on our solution to the previous example. So here was our augmented matrix that we had. So let's move 2 equations. The first row says 1x1 plus 0x2 plus 2x3 is equal to -3. The second row, x2 minus 4x3 is equal to 1. So x3 in this case is going to be our free variable. It can be any value, and this is the idea of a free variable. We can pick any number we want for x3. Once we pick a number for x3, it will define a particular solution. In particular, x2 would be 1 plus 4x3, and x1, -3 minus 2x3. And these came from solving the equations from the augmented matrix. So in particular, you can pick x3 to be any variable you want. x1 and x2 will be defined based on that. And we have infinitely many solutions because every possible number that you pick for x3 would give a solution to this system. So let's do another example. This one is a system of 2 equations and 3 unknowns. So let's start with the augmented matrix. Once we have that, and we already have a 1 in the first row, first column, we need to turn the 2 underneath it into a 0. So we'll do -2 row 1 plus row 2. And based on this row operation, you can see that it is impossible to get a pivot in the second column. So this time, x2 is going to be our free variable. We do continue row reducing, however, and we're going to do 1/2 row 3. Since we can't get a pivot in the second column, we'll move to the third column. The final step would be to turn that -2 into a 0, so we'll do 2 row 2 plus row 1. And here's the result. Since there's no pivot in the second column, we know we have infinitely many solutions. In particular, we can write this as x1 minus 3x2 equal to 1, and then the second row said x3 is 5. So we start by solving for x1. So x1 is 1 plus 3x2. x2 is our free variable, so it can be any value we want it to be. And then x3 is always going to be 5. With this comes our existence and uniqueness theorem that says if we have a linear system, it will be consistent if and only if the rightmost column of the augmented matrix is not a pivot column. If it is a pivot column, then we have something of the form where everything to the left of the augment is zeros and to the right is not a zero. That would be not a solution. Inconsistent just means we have at least one solution. So therefore, this theorem is satisfied.